Hey everybody, welcome back. Mr. Smith here. In today's deck, we're going to lay out the key skills that you need to be able to work with velocity graphs and apply those things to the situations you're going to see in class. We're going to give you all the basics right here, so tune in and pay attention hard. Before we do, I'm going to give you a background review on what we learned when we talked about constant motion graphing. So if you remember, we began the year by moving in front of a motion detector. Here was our motion detector. Little box. We were walking out in this area out here, because the detector had no negative side to it. Everything we did was either walking away from the detector or walking towards the detector. So what's going on? Motion A, you're standing 2 meters from the origin, where the motion detector lives, and you walk out to a position of 10 meters. So that's motion A. You noticed you're moving in the plus direction. Graph climbs, graph goes up. You're moving to the right in our lab. That's what the positive direction was. Later, you turn around and you walk from 10 meters on back to around 4 meters in section B. You were walking in the minus direction. How could we tell? The graph was declining. What I wanted to do right now is explain something to you. We left ourselves open to a little bit of a problem, and it's in the language. If we use the words towards and away from the detector, that gets very confusing. And so starting right now, what I want you to do is to shift your language to the idea of using positive direction, negative direction. It turns out it's actually simpler, and I'll give you an example of why right now. This is you doing motion C and D. What's going on right here is we're imagining that the motion detector actually has two sides. So this side of the motion detector is the plus side, and this is the negative side, but watch the motions. Here, you start at the origin, so you start at the 0 of position, and you walk your way down towards minus 8 meters. So you end up down here. If you're thinking about this, you should say, oh yeah, you moved in the minus direction. Also, do you understand? You moved away from the detector. So away from the detector is a bad word because it can mean two things. If you have a two-sided motion detector, like an ideal one would be, moving in this direction could mean two things. So we're going to simplify that and say, do you see the graph dropping? Do you also agree that you're moving towards the left? Make it easy. Anytime you're moving towards the left, we're going to call that the minus direction. Anytime you're moving towards the right, it's going to be the positive direction. So check out section D. Here you move from minus 8 meters back to the origin, and you do it pretty quickly, and boom, that's moving in the plus direction. So it should be simple. Graph going down, minus direction. Graph going up, plus direction. That's what we needed to know from a position time graph. Thing number one, anyway. Thing number two is right here. We talked about how the slope of the position time graph gives us the velocity, and it's just important to remember slope equals displacement over time for a position time graph. So we move from a position of 2 meters to a position of 10 meters in 4 seconds. That's what section A is. So what do we do? Your displacement is 10 meters minus 2 meters. You moved plus 8 meters, and you did it in 4 seconds. So we figured out your slope was your velocity is 2 meters per second. You can do the same thing with B. The thing I want you to notice is, do you again see the plus sign coming out and the minus sign coming out really naturally? So you'd say I moved in the plus direction at 2 meters per second for this whole time. And for this whole time, you'd say I moved in the minus direction at 1.5 meters per second the whole time. Okay, so constant slope, constant velocity. What I want to do is show you how that translates to a velocity graph. What we do is very simple. We take these slopes that you just looked at and we use them. So the slope that we just looked at, where we said plus 2 meters per second, was constant. And if I change the graph from position to velocity, you're going to see that my plus 2 meters per second is just a constant speed, constant, so nice and horizontal and flat. Same thing down here. We said that your velocity here was minus 1.5 meters per second, constant velocity, a nice flat horizontal line. Right. The shapes of the graphs look different, whether it's a position or a velocity graph, for sure, but the motion is the same. So the next thing you want to look at is, how do we use these graphs to solve problems? Concept number one we've already talked about is that the slope of a velocity time graph gives us the acceleration. And so we've got a situation here that's pretty simple physics problem. Claudia accelerates her bike from rest to 8 meters per second in 6 seconds. So what that's going to look like on a graph is just like this. And what you're going to do with that to solve it is just go ahead and get the slope. So the slope of this graph is going to equal the rise over the run. And what I'm going to do is just go ahead and figure that out. So the rise of the graph goes from 0 meters per second all the way up to 8 meters per second. So it's the change in velocity. So it's 8 meters per second is the final velocity minus 0 meters per second was the first velocity. So change in velocity. Then divide it by the run, which is 6 seconds. And if I do the math, I get 1.33 meters per second. Watch the labels. There you go. The slope of the velocity time graph gives you acceleration. The second kind of question you're going to do has to do with same problem, but they're asking us for something different. So Claudia accelerates her bike and they ask her, how far did she go? What's her displacement? So what I'm going to do is use the exact same graph and use a fact that the area between the zero line of velocity and the graph that we get is called the displacement. Okay, so second key fact. So what I'm going to do is take this graph and I'm going to go ahead and shade in the area that this shape makes. And all I have to do is go back to basic geometry and say, well, okay, I know the area of that triangle is 1/2 of base times height. And now the base and the height are real things. So the base is going to be 6 seconds. So put the 6 first. And the height we just talked about is going to be 8 meters per second. And if I go ahead and do 1/2 base times height, I go and figure out that the area of the shape is 24 meters. So what does that mean? Is that even though she wasn't going constant speed, we can easily figure out how far she went as she did the motion if we just know this trick, that the area of the VT graph gives us the displacement. So let me show you one more complicated example that uses that. So what they say now is Claudia continues her story and then rides at steady speed for 2 seconds and finally slows down at a rate of -4 meters per second. And they want us to figure out how far did she go during the entire 10 seconds of motion. There's two things you're going to get here. First of all, let me show you the graph. This we just copied. You should know this now, that if Claudia continues her speed for 2 seconds, the velocity line just goes flat. So she's moving, 8 meters per second for 2 seconds. And then thing one, she slows down at -4 meters per second. So what that means is that for every second that goes by, her velocity slows down by 4 meters per second. So you can see between 8 and 9 seconds, her velocity drops from 8 down to 4. She lost 4 meters per second in that 1 second. And then she does it again. So it should make sense that if you have 8 meters per second of speed, you're going to lose it in 2 seconds with an acceleration of -4 meters per second. Okay? Let's close it out. We know for a fact that the area of this first shape is 24 meters, so we don't need to go ahead and figure that out again. But what I am going to do is take this complex shape and chain these areas together. So I know that during this time right here, she was going steady speed, so that makes that a natural area that I'm going to shade in and figure out. Then what I'm going to do is go ahead and color this one over here red. I'm left with a triangle over on this end, and I can go ahead and figure out the area of that shape. And how far did she go overall? It's just going to be what you get when you add all the things together. So just use what you know from geometry. If you have a box, the area equals base times height. So the area of this middle shape is going to be, let's see, 8 meters per second. That's the height times the base is 2 seconds. And I get that she moves 16 meters during that middle section. Okay? Then what we're going to do is go back and grab our red here, and we're back to using area of a triangle. So 1/2 base times height for this shape is going to give us 1/2 of 2 seconds, and the height again was 8 meters per second. And we go ahead and multiply all these out, and we get 8 meters total. So what do? Well, if you want to figure out the overall area that she did, We have 24 meters here, 16 meters there. Add those together, you get 40. Tack on the 8, and overall, the displacement that she had is 48 meters. So what we've done, two key concepts. The slope of a velocity time graph is acceleration, and the area between the zero line right here and the graph line is called displacement. Okay? Those are your key things. Practice with them. Bring your questions to class, and let's talk soon. Take care. Thanks for watching. Bye-bye.